Welcome back to ECE 441A 541A. In this video we're going to be talking about steady state error and system type when we're dealing with control systems, and in particular it would be nice if we could start to become a little bit more comfortable with interpreting this table that's in the textbook and understanding exactly what it's saying with these infinities, with zeros. But here you can see that we have different types of inputs that are being applied to the system. We actually have, in this first column, we have a step input. In the second column, we're dealing with a ramp input, and in the third column, our input that's being applied to the system is parabolic, or a function of t squared in time. And what we want to do is actually start to become comfortable with saying, oh, we have a system that's type 1, but we need to understand what it means when we say our system, or the number of integrations in g sub cg, is 0 or 1 or 2, and that will then lead to a particular type of steady state error based on what particular input we're applying and what the system type is, type 0, type 1, or type 2. Hopefully then by the end of this video you will have a little bit better understanding of what we mean by a system type and what that implies relative to steady state error, or the accuracy of our system in the steady state. Let's start actually by asking a question. And the question is, and now you may already be preempted a little bit after thinking about the table entries, but what comes to mind when you see this expression 1 over s? Most students, I think, will start to see that and say, oh, that's the Laplace transform of a unit step, where we now are thinking of the time domain counterpart to 1 over s corresponding to a waveform, and that waveform is a constant of value 1 for all time t greater than or equal to 0. So when you see 1 over s, you might be thinking of a signal or a waveform, and in particular, since it has a gain of 1, the numerator is 1, then we actually are looking at the unit step. Another possibility for this 1 over s expression is actually to view that as an operation in the s domain. And when we have an operation in the s domain, then we know now, based on what we've been talking about in this class, that in the time domain, that now corresponds to an integration operation. Now, if you see that 1 over s, you could also be seeing that as an operation, an integral operation, and what that means then is something different. Now we're viewing that 1 over s as if it were a system and not a signal. So what 1 over s corresponds to really is what it's trying to represent or model in the time domain, and we can view it either as a signal or as a system, and how we interpret it depends on the context. So now let me state the following fact. A fact is that using pure integrators, so now when I'm saying using pure integrators, I'm saying maybe put this in your block diagram, this 1 over s, or introduce a pure integrator in your all integrator block diagram. Using pure integrators can be very beneficial when trying to improve the steady state accuracy, or when you're trying to achieve small steady state error in the system. What do we mean by steady state error? Well, that typically will depend on how your system is interconnected, or the different pieces that are making up your overall system. Here is a more elaborate interconnected block diagram. You have your plant, G of S, you have your controller, G sub C of S, you have possibly feedback dynamics, H, and you have a precompensator, G sub F. This G sub F is then a gain or even a transfer function that's going to adjust the reference input signal even before that signal's value gets compared with the output, filtered output, where the output is filtered through H of S. Let's now look at what this would look like if now somebody said, well, what's the steady state error for this configuration of a controlled system? Well, the steady state error typically is how does the output Y compare to the reference input R? And in that case, we can see that this is a little bit more than our generic cheer, because we have a G sub F in there, we have a G sub C. If we simply looked at the transfer function initially from R sub 1 to Y, now that looks more consistent with what we're used to seeing. Meaning now maybe we can look at just deriving the transfer function between R of S, or R sub 1 of S and Y. And if we do that, now we can impose cheer 1. So R sub 1 is this signal immediately to the left of the summing junction. Now we simply have G sub C G over 1 plus G sub C G H. That's our cheer. That's T1. But now we can simply say, oh, but R1 can be written in terms of the actual reference input, R of S. R sub 1 is the output of that block, G sub F. So R sub 1 of S, Laplace transform of that signal, is now G sub F R. We can plug that into our expression for Y, and we see that Y is now T sub 1, G sub F R of S, or that really says that this pre-compensator, G sub F, is now going to appear in the numerator of our original T sub 1 of S expression to give us our overall transfer function T of S between the reference input R and the output Y. That's now what the transfer function closed loop would look like based on this particular block diagram configuration. Once we have that transfer function, we can now use that in our error expression, which compares the reference input R to the output Y. That's just R minus TR. We can pull out a common R, factoring out 1 minus T of S in our E of S expression, and then we can actually use the final value theorem to help us look at one point in time without having to do too much solving. We don't have to inverse Laplace transform. We can just look at the limit as S goes to 0 of S times what's in this bracketed expression, 1 minus T of S times R of S. And obviously this error will depend on the type of system that we have that is maybe described by G sub C and G, and it will also depend on the waveform that we're applying as our reference input, capital R of S. That's how you could formulate this for a fairly generic block diagram with several different blocks explicitly identified, and now you've derived that relationship, and you could solve for the steady state error given a particular G sub C, G, G sub F, and H, and a particular reference input R of S. Obviously though, the final value theorem would have to be, or we could apply that only as long as the closed loop system is stable. So that's an assumption that we would be making in applying the final value theorem. if our closed loop system is not stable, there's no reason to even expect a steady state error. Our signals are going to go unbounded. So we have to have our system being stable in the closed loop. Let's now look at this steady state error behavior relative to specific G of S's or plants, and let's look at this using some of the earlier plants that we've used in previous lectures. And we're going to simplify our block diagram. There's no pre-compensator. We've collapsed everything that was in the forward path into one transfer function, G of S, and our feedback path is unity. So we have negative output feedback compared with the reference input signal. And now let's go ahead and just assume that the reference signal, instead of just being a unit step, if we put A in the numerator of that expression for R of S, now we have capital A over S, and that just means that we're looking at a constant input, or the reference input in the time domain, R of t, is equal to A, a constant A, for t non-zero. Or I'm sorry, non-negative. Again, we can derive that expression for E of S. E of S is R of S minus Y of S, but Y of S is just G of S E of S, and now we have an equation, one equation that only involves R's and E's and all the transfer functions in the expression. We can factor the E of S out of those two common terms. We have 1 plus G of S E of S equaling the reference input R of S, and now we can divide both sides by 1 plus G of S to end up with our transfer function between the reference input signal R of S and the error coming out of that summing junction now as E of S. Remember our plants or systems that we've looked at in previous lectures. Here our G of S is first order. We have a polynomial that's linear in S in the denominator. We have a gain k sub 0 equal to 10 in the numerator. Our time constant tau sub 0 is 1. And now I want to emphasize the use of this descriptor of a type 0 system. A type 0 system means that we have 0 integrators, pure integrators, or we have 0 poles at the origin in this particular system, G of S. We don't have an S all by itself like that in our denominator. That would, if we had that S sitting there, then this would be a type 1 system. We would have a pure integrator in that system. At this point, we do not in this specific G of S. Now, for this combination of gain and time constant, our closed loop system is stable, so we can apply the final value theorem. You would have to check that, but I've already done that, so I'm going to avoid that step. And now what I want to do is examine the steady state error for this particular combination of gain, k sub 0, and time constant t sub 0. The expression then, using the final value theorem, is the limit as s goes to 0 of s times E of s, but E of s is just 1 over 1 plus g times R of s, and in this case we're saying let's go ahead and let the reference input be a constant a, and so now its Laplace transform is a over s. Here is our capital R of s. If we now look at what we have, that s cancels that s, and we can now look at sliding that a inside the parentheses, and we have capital A over 1 plus g of s. And we're going to look at the limit as s goes to 0 of that expression. Doing that, we now see that we have a over 1 plus g of 0, and in fact we are going to go ahead and call that g of 0 k sub p. We're going to give that its own descriptor or identifier, and we're going to call that k sub p the position error constant. And what is k sub p? Well, that's just g of 0, but you know what this is. G of 0 is just the DC gain of that system. So now let's see what that actually equals for this particular case. We have tau sub 0 equal to 1, k sub 0 equal to 10. G of 0 is now going to be k sub 0 over tau sub 0 s plus 1 with s equaling 0, or that now becomes k sub 0, which is 10. So in this particular system with these parameters that we are using, k sub 0 equal to 10 and tau sub 0 equal to 1, we now have an air steady state equaling 1 over 1 plus k sub p. The position error constant is this k sub 0 in this case, which is 10. We now have an error, steady state error, due to a constant, and now maybe what I've forgotten is this a for our input amplitude. So let me go ahead and say that that's now a over 11, and now we have this is going to be less than 1/10 of a. So we put in a constant of a for our reference input, and the error between the reference input that we inject into the system and the output itself is 10% of that. So we're within 10% of the initial reference input value at the output waveform y of s. So now let's look at system B that we've looked at before, and system B now is simply g of s, the same structure that we had for A, but now we have a k sub 0 equal to 1 and a tau sub 0, our time constant, is 1/10. All of the formulas are going to be the same structurally, and so our steady state error for this particular system. And what type of a system is this? Is this a type 0? Is it a type 1? It's actually a type 0. There's no pure integrator in that system. So now we can use the air steady state expression 1 over 1 plus k sub p, which is 1 over 1 plus g of 0. In this case, well, again, if I put in a constant of a, then I have an a here if I'm comparing apples to apples. Now I have a over 1 plus 1, and this now becomes 1/2 a, or now the steady state error is 50% of the value that we injected to begin with, which is quite a bit bigger than the error that we had in part A. Part A, it was within 10% of the magnitude of the reference input. Now the error is 50% of the magnitude of the input that we applied. Let's now look at system 3, which was part C that we've been looking at. So now g of s in this case is going to be 1 over s plus 1. And now I hope you can see that in this particular case we do have one integrator, pure integrator, in that system, or we have one pole at the origin. That's what we mean when we say we have an integrator. We have a pole at the origin. If that was an S squared, then we would have two poles at the origin, and it would be a type 2 system. This G of S is now a type 1 system. Let's look at what the steady state error is for this particular case. The steady state error, and now we're assuming our closed loop system is stable, and we could verify that, but I've already done that, so I'm going to skip that step here. But in reality, we would be wanting to check that. Let's now look at using the final value theorem, which says now that we need to look at the limit as s goes to 0 of s e of s. And in this particular case, for this particular plant, we have 1 over 1 plus G of S times R of S. And if we let R of S again be our constant input of, let's say, A, so it now becomes A over S. This S cancels that S, and we now have something that looks a little different than what we had before when we start substituting in our explicit expression for G of S. Now we're looking at the limit as S goes to 0 of 1 over 1 plus 1 over S, S plus 1. And now we have something in the denominator of the denominator. Let's clean that up a little bit. I'll do that in a couple of steps so that you can see where this is coming from. Let me put the denominator over a common denominator. And now let me move that denominator of the denominator upstairs into the numerator. And if I now let the limit, or let S go to 0, you can see that the denominator is well behaved. I have a denominator that in fact goes to 1, the numerator goes to 0, and now I have 0 for my steady state error. And the connection that I'm wanting you to draw from that is now we had one integrator in our open loop system, G of S. That type 1 system now allows us to actually annihilate or completely eliminate errors due to constant inputs. It really didn't matter. In this case, actually I forgot my A, so let me go ahead and put the A in here. That A, you can see, doesn't really matter what that constant was. I'm still going to go to 0. And the reason behind that is because we had this integrator, or this pole at the origin, in our original system G of S, and that pole at the origin actually helps drive this steady state error, drive the error to a steady state value of 0. So it helps drive the error to 0. To emphasize that, this type 1 system in fact will give us 0 error steady state for a constant input obviously we're assuming that the closed loop system is stable, or we wouldn't be able to make that conclusion. Now, if we compared the DC gain of this G of S, 1 over S times S plus 1, with the DC gain of those earlier type 0 systems, Now what happens as we let s go to 0? Well, now this is actually undefined, or it goes unbounded, or it gets really, really big, is one way to think about it. And now what we could do is we could say, okay, now that we have this nice behavior due to constant inputs, what happens if I put in a ramp? Or what happens if I now change the reference input to being a function of time, a linear function of time, instead of just being constant? That now introduces one more air constant called the velocity air constant. We had our position air constant. Now if we're putting in a higher ordered polynomial for our reference input, now it's linear instead of 0th order. Let's now look at the velocity air constant for a type 1 system. In this case, the velocity air constant is actually defined by k sub v as the limit as s goes to 0 of s times, and now let's go ahead and assume that we've parameterized our forward path to be consisting of a controller g sub c and a plant g. That's now the generic formula for the velocity air constant. In our particular third case, where we were dealing with system C, k sub v, the limit as s goes to 0 of s, 1 over s, s plus 1, that was our g of s. This is now, those s's cancel, and we now have 1 over 0 plus 1, or 1, for our velocity air constant. So now let's look at what happens if that's now a velocity air constant and we're interested in applying ramps or linear functions of time to these three systems. Let's examine what happens to these systems if we apply a ramp. Let me say r of t equal to at for t greater than or equal to 0. That's what I mean by a ramp. A reference ramp input, r of t is equal to at to these systems. Suppose now we look at the first system where we had g of s equaling k sub 0 over tau sub 0 s plus 1. What was the system type for this system? Well, it was actually a type 0. The air expression is still the same, even though our r is different. We now have 1 over 1 plus g of s times r of s. It's r of s that's now different. Now we're saying r of t is at, but that in the frequency domain transfers into, or Laplace transforms into, a over s squared. If that's now our reference input, our expression for the air signal, E of s, now becomes 1 over 1 plus k sub 0 tau sub 0 s plus 1 times a over s squared. Or, if we simplify this out a little bit, then we end up with a times tau sub 0 s plus 1 over s squared times tau sub 0 s plus 1 plus k sub 0. Or, if we wanted to, we could factor out of this a tau sub 0, and we now have s plus 1 plus k sub 0 over tau sub 0, and now it's in a factored form where we can explicitly identify our pole. If that's the case, what would we do if we wanted to inverse Laplace transform this expression for E of s? Now we would simply do a partial fraction expansion. Our denominator has a linear factor, s plus this, let's say, pole location P1, which is this, and we have two poles at the origin. So that now I have, for a partial fraction expansion, I have alpha 1 over s, alpha 2 over s squared, plus an alpha 3 over s plus that pole location 1 plus k sub 0 over tau sub 0. And hopefully you remember how to inverse Laplace transform this alpha 1 over s in the time domain. That's just going to be a constant alpha 1. The alpha 2 over s squared is now alpha 2t, and this alpha 3 scales this exponential piece where the exponential sigma is related to our pole location. Our pole is now at minus this sigma, but sigma is 1 plus k sub 0 over tau sub 0. And what does this say about our steady state error? Now, if you wanted to sketch this error, or if you said, oh, I actually have, in terms of a time response, I now have a ramp. Let's say this is now at, but the error is now, if you look at that, that's going to grow with time t. The error signal is going to grow with time t, so that if I wanted to see what the y is doing, it's now not keeping up this particular error between the reference, this is r of t, and this red is y of t. This error, e of t, grows as a function of time because of that alpha sub 2 term, alpha sub 2 t term. Meaning, this particular system, type 0 system, when we apply a ramp input, is in fact unable to keep up with or to track the ramp input. The error between where we want, r of t, and where we are actually at, y of t, grows as a function of time. So now that's going to be true for the plant from part B as well. So now let's look at what happens for a different system type. What's the steady state error, or is the steady state error bounded with our third plant that was in fact a type 1 system? And we're going to apply again a ramp input. So in the frequency domain, r of s is a over s squared. This is our system C, which is a type 1 system. And again, we have to make sure that our closed loop system is stable, and it is. Again, we would need to verify that, and we'll talk more about stability with Ruth array and Hurwitz criterion, etc. But the error expression here is again 1 over 1 plus g of s times r of s using the final value theorem, we now have the limit as s goes to 0 of s, and we have 1 plus 1 over g of s. Our input Laplace transform is a over s squared. We can push through some of the algebra, and in fact what we end up with is a over the limit, or let me just go through this a little bit more slowly. We have one of these s's canceling that s, so that now we have the limit as s goes to 0 of a over 1 plus g of s, but this is now times s, which was left over from that. And now as s goes to 0, this s actually distributes. We have an s there and we have an s there, and remember what we said we had before. Well, this particular s is going to go to 0 as we let s go to 0, so this now becomes in the limit a over 0 plus the limit as s goes to 0 of s g of s, but this particular term is what we were calling our velocity gain constant or air constant, and that for this particular case, remember what it was? Case of v was now the limit as s goes to 0 of s g of s. There's our g of s for this particular system, or that's now just 1. So now our steady state air is in fact going to be a over 1 or a. So now our steady state air is bounded. It's at a, it's not growing with time, but there is an air. But now we might have our ramp going up like this, but now our y of t is going to be within a of that particular signal. So we do have a bounded air. Our system was a type 1 system, and that now allowed us to have, as long as our closed loop system was stable, it allowed us to have a bounded steady state air due to a ramp input. And that's really what this table is saying. For systems of type 0, we will have a bounded air only for constant inputs. And here is the expression that we derived ourselves, a over 1 plus k sub p, where k sub p was that position air constant. When we had a type 0 system, on the other hand, when we had a type 1 system, our air due to a constant was 0, but now we had a bounded air due to a ramp input, and that bounded air was a over k sub v, where a was the value of our slope on the ramp waveform. Then if we go up a notch and add a second integrator, then we have a steady state air of 0 to a constant, steady state air of 0 to a ramp, and we have a bounded air due to a parabolic input, but we have infinite air if we were using a type 1 or a type 0 system. That's now how you can interpret this table, but I would suggest that you work through the analysis at this point until you become very comfortable with associating the system type, which depends on this forward transfer function in our block diagram. What is its, how many integrations are present, pure integrators, and what is the corresponding air due to the appropriate input type, whether it's a step, a ramp, or a parabola. That's important to know. System type, reference input behavior, and then what is our steady state accuracy. And this table does a good job of summarizing that information.